Okay, were there any questions over the homework? Yes? What do you got?
Part B number 5.
Part B number
Page 61.
16. Negative 12 plus or minus that thing? Okay. Negative 12 plus or minus square root of negative 36 over 4. And you're asked to simplify, right? All right, so first of all, see the square root of a negative number, right? Square root of negative. We talked about that last class, that negatives under the root means that we're going to have to split it up into negative 1, root negative 1 times root 36. And the square root of negative 1 is I, so this becomes I. And then the square root of 36 is 6, so that would just be 6I. Agreed? So I could rewrite this as negative 12 plus or minus 6I over 4. And then at this point I can go a little further, because I recognize that 4, 12, and 6 all have a common factor, right? What number goes into both 4, 12, and 6? 2. So I can reduce everything by 2. Now technically, if you want to know what's happening here, is you're factoring a 2 out of the top, right? I pulled a 2 out, and on the bottom I rewrite 4 is 2 times 2, and I'm canceling a factor of 2. But most people don't write that down, all right? They just say, okay, 2 goes into 4 twice, 2 goes into 12 6 times, 2 goes into 6 3 times, and so you get the negative 6 plus or minus 3I over 2. Does that make sense? Yes? One thing to be careful with here, you are not allowed to, at this step, say, oh, 4 goes into 4 once, 4 goes into 12 3 times. You're not allowed to do that. The reason why is because in order to cancel a factor like this, if you have 2 terms up top, addition or subtraction, then you have to be able to cancel it with all the factors. With this, I'm sorry, with all the terms. This one, and this one. So that would be a mistake. Got it? Any other questions? We're good? All right, what were we doing last class? We finished up at the end, and we had established the formula, right? The quadratic formula, which I'll write down on the board off camera here. The quadratic formula was a formula that allows us to solve any quadratic equation that looks like ax squared plus bx plus c equals 0. And the formula is that the answers will be negative b plus or minus the square root of b squared minus 4 times a times c, all of this divided by 2a, right? That's in your notes. What I'd like to do to start class is just solve a quadratic equation using the formula. And then after we do one of those, if everyone feels comfortable, we'll move on to the goal of today, which is to actually sketch or graph quadratic functions or quadratic equations. So let's do a solving of a quadratic here. And I don't want to do the homework one. Let's do this one. Let's solve 4x squared minus 1 equals 6x. So when we look at this, we're asked to solve, right? And we have to identify what type of equation we have. This is a quadratic equation because of what? That doesn't make quadratic though. The x squared. The x squared and then the equal sign. Equal sign makes it an equation. The x squared means it's quadratic. So what we're going to do is we're going to try and see, is this the one where we had, remember there were different cases I gave you last time? Are we missing the x term?
No.
No, we have an x term. Are we missing the constant term?
Yeah.
We have a -1 here. You see, so that would be a constant term, so we're not missing a constant term. That means we have everything. We have the x squared term, the x term, and the 1. And the constant, sorry. So what we're going to do is move everything to one side of the equation to start. And the goal is to get a 0 on one side. So I'm going to subtract 6x here and subtract 6x here. That will give me a 0 on the right side. And on the left side, you tell me what I would have. 4x squared minus 6x minus 1. And we put it in descending order, which means highest power of x first. So there's your highest power of x. The next highest power of x is the minus 6x, and then minus 1. So the powers of x come down. That's called descending order. Once it's in descending order, it looks like this, right? And we can identify a, b, and c, and we could use the formula, couldn't we? But before you go trying to attack this with the formula, you might just want to check to see, does it factor? If it factors, that might be faster, especially if you've gotten good at factoring. So does this one factor? Let's do a quick check. We would take the 4 in front, the -1 in the back. We multiply those. We get -4. We look at the number in the middle, -6, and then you try and come up with two numbers that multiply to be this and add to be this. Not happening, right? It's not happening. So this would fail. Since that fails, in the past we would try and say something like prime, but this is an equation, right? And all quadratic equations we can find answers for using this formula. So if I'm going to use the formula, I should probably take some time to write down what a, b, and c are. That way I can use the formula. So what is a for me in this problem? 4. So that's the number in front of x squared. B, -6, and c is -1, right? And now it's a matter of just plug and chug, right? You just plug that in there and see what we get. So I'm going to write down x equals. Very important that you write down x equals. And then this was kind of confusing people last class. We have -b, but our b is already negative, right? So it's going to be negative of a negative, which is positive. So I'm going to put just 6. Plus or minus square root. And I told you something about this next number. It's always positive. And it's going to be your b squared. So what happens if you square the b over there? What do you get? 36, right? -6 times -6 is positive 36. Minus 4 times, I'm going to write it out, a, which is 4, times c, which is -1. All of this over 2 times a, sorry, I don't know why I put -1. 2 times a, which is 4. We all good with that? Okay, now let's continue. I also said Tuesday, that this is a part that most people make mistakes on the computation of this. I suggested that you just cover up the minus sign and multiply those numbers together. 4 times 4 times -1, which would be -16. And you're going to subtract that. So I'm going to write it down, just like I said it. I'm going to have 36 minus, and I'm subtracting -16. Then all over, let me go ahead and multiply the bottom. 2 times 4 is 8. Y'all agree? Minus a minus really means positive or plus, so that's 36 plus 16 all over 8. 36 plus 16 is 52. Square root of 52 over 8. That's where we are right now. Now that would be correct on a test. If I gave you this problem, I said solve this quadratic equation, that would be correct as long as that 52 can't be broken down further. So this is what we started class with last time. to see if I can break down 52, I start to try and divide it by perfect squares. Remember that? So does 52 break down? What goes, how can you rewrite it? Do any perfect squares go into it? I know that you can break this down to be like 2 times 26, right? Something like that. But, okay, so 4 and what? 13. 4 and 13. So what we're looking for is, does a perfect square go into this? 4 and 13. Okay? And 13, does that break down? No. So I could rewrite this as 6 plus or minus square root of 4 times square root of 13. So I use that property from last class that if I have a root of a number, if I split the number, I can split it in 2 roots. Square root of 4 is 2. So this just becomes 6 plus or minus 2 times the square root of 13 all over 8. There's one more thing I can do. It relates to the question that was asked at the beginning of class here. 8, 6, and 2, right? 8, 6, and 2 all have a common factor of 2. So I can reduce this by a factor of 2, this by a factor of 2, this by a factor of 2. And I can ignore the 13, because it's attached to that through multiplication. I can just ignore it and just work with these 3 numbers. Okay? So 2 goes in here how many times? 3. 2 goes into here how many times? 1. 2 goes into here, 4. So my final, bless you, well, it's almost my final answer. 3 plus or minus what? 1 times root 13, right? I don't have to write the 1, because 1 times anything is the anything, right? So I can just write 3 plus or minus root 13, and then over 4. And that, we would box that normally and be happy and be done.
What if you, with the 6 plus or minus the square root of 52 divided by 8, what if you factored that before you did that?
The 2, like a 2 here, 2 here, 2 here? Good, very good question. You can't, because there is a factor of 2 in here, I agree, but it's underneath the root. Okay, so it's trapped. You can't cancel. Remember what I said in the last problem. What I really did technically here on this 6 plus 2 root 13 over 8, what I really did was I pulled a 2 out of the top. And if I pull a 2 out of the top, it would be 3 plus 1 root 13 over, I could rewrite the bottom as 2 times 4. And then I'm canceling the 2's. So when you come here and you say, you know, like 2 here, 2 here, 2 here, if I were to do it here, 2 here, 2 here, 2 here, it's actually not a 2 here, it's under the root. You would have to look at that 2 as being a 4 first and bringing the 4 out. I don't know if that makes sense. Not really? Okay, let me try and think of a better way I can do this.
So as long as it's like inside square root,
You cannot reduce it.
unless you,
Unless something pops out, okay, like the 2 popped out, then you can look at these numbers. Another way I might be able to explain it is to say this. Just look at that right there. If you were to cancel these right now, okay, say, there's a 9 there, 9 there, what would your answer be? It would be square root of 1 over 1, and you'd be telling me that that's equal to 1, right? But really, like, ignore this. What's the square root of 9? 3. So this should be 3 over 9. That should be 1/3, right? So this thing of canceling these is not allowed. However, if I had first, well, yeah, does that illustrate it?
yeah.
Okay. Yes, it's protected by the little root. You can't cancel factors through the root. You have to take care of it and bring something out first. Okay, so this answer would be correct. We would be done if that's what we are being asked to do on the test, right? Which is what you'll be asked to do. But because of where we're going, I'd like to do one additional thing to this. I'd actually like you to get on your calculators and tell me what the square root of 13 is. And let's just get it like 1 or 2 decimal places. So So what is it?
3.60.
3.60 approximately. So what we're going to say is that this is approximately 3 plus or minus 3.60 over 4. And remember that that plus or minus means we have two answers, right? Two different answers. We have to look at the plus as one answer and then the minus as a different answer. So what I'd like for us to do now is figure out what those two answers are. And the way I do it is I just break this into two things. I'm going to look at the plus case and then I'm going to look at the minus case. So if it was plus, it'd be 3 plus 3.60 over 4. And when we do that on the calculator, you must do the numerator first, okay? That would be 6.60. Divide that by 4 and give that to me as a decimal. What do you got? 1.65 about? Okay. Understand? And then if I do the minus, it would be 3 take away 3.60 over 4, which would mean negative 0.60 over 4, which would be negative 0.15. These two answers are what we call the approximate answers. Those are our approximate answers. This right here is called the exact answer. And the difference between the two is that when you give someone the exact answer, there's no rounding that ever took place. There's no error, okay? There's no error. There's no error in this expression. That is the exact value. Over here, when I use this squiggly equals, it's because that 3.60, it wasn't 3.60, it was like 3.60 something, right? And it kept going. And so at some point I had to stop. And as soon as I stop and cut off those other pieces, I create error in the problem. And so these answers are close to the true answers, but they're not exactly the true answers. So maybe if I'm trying to build a doghouse, okay, and I'm cutting wood, and I need it to be 1.65 inches, I can get close enough, right? It's a doghouse, right? Now if I'm building, you know, like bearings that are going to go into the engine of an aircraft, and it needs to be 1.65 millimeters, dead on. I've got to be a little more precise, right? Like I need to make sure it's 1.65, not 1.654, not 1.647, right? Because we're talking about tolerances that could cause the engine to come apart in midair, right? I mean, so in the real world, this is a perfect answer. We have to, at some point, estimate it. And how far you go out depends on what you're trying to do. Building the doghouse, hey, I just got to get close to 1.5 inches or whatever it is, you know, 1.5 feet. Building aircraft, tolerances have to be, well, it's all listed. When they build aircraft, they say what the tolerances are allowed to be. You know, you're allowed to be off by, you know, 1/10,000th of an inch or something like that. They use like lasers and stuff to verify. All right, understand the difference between the two answers? Exact, precise, perfect answer approximations. But we are going to use these today, all right? Because I bet when you looked at that, you had no idea that that was 1.65, all right, and negative 0.15. Like you look at this, you could really have no clue that those numbers even were close to those, right? So we use this because it's easier to visualize what they are. All right, I think I'll do one more. Let's do the same problem I just did, but I want to change. Let me see. Well, you know what? I'm not going to be able to make that happen. No, I think we're okay. I'm wondering if I should give you one with a fraction. Let's do one with a fraction. Okay, x squared minus 3/4 x plus 1 plus 1 equals 0. Solve this. All right, this is a quadratic equation, right? Are we missing the x term? No. Why am I asking you that?
Because of the case number 1.
Yeah, if we were missing the x term, like if this wasn't there, right? If that wasn't there, then our method of attacking this problem would be just to move the 1 over and then take the square root on both sides. The method would be completely different than this. And then the second thing is, are we missing the constant term? Which we're not, right? But if that wasn't there and all we had was that, how would we solve this? Case 2, we would just factor out an x and then set both of the factors equal to 0. So the approaches for the first two methods are to save you time, much quicker than this. But because we have all three things there, right? The x squared term, the x term, and the constant, since they're all there, I'm gonna use that method. Now, I could right now, if I want, write down what a, b, and c are. But then that means you're going to have to work with fractions, right? Are you prepared to work with fractions? Are you okay with that? You all right with that? All right, one other option you could do is this, and I'm just going to write it down. I want someone to tell me what I did. Yeah, I multiplied both sides of the equation by 4. Why did I do that? Because I didn't like that denominator. And because I have an equation, I can multiply both sides by anything I want. I chose to multiply by 4. If I multiply, I distribute through 4, right through everything. This creates 4x squared. Cancels the 4 here, leaves me with a negative 3. 1 times 4 is 4. And then on this side, I have to do the same thing, but 0 times 4 is still 0, right? And look at this equation. No fractions. So let me ask you again, I'm okay with working with fractions, but would you prefer to stick with that, or do you want to go and use this one? Left or right? I have one vote for right. Right. You said left?
I'll go right.
You go right? Okay, so we're gonna do this one, all right? Now, what's kind of amazing here is that the answers to this equation, the solutions, are exactly the same as the solutions to this equation. Does it seem like it would be? Yeah? I mean, to me, if I multiply this by 4, then my answers are maybe like 4 times bigger than those answers. But that's not the way it works. Because you're multiplying both sides by the same number, okay, you're keeping the balance to the same, and the solutions here will be identical to the solutions there. We could check it if we want, but let's just work through this one. What's a, b, and c? 4, negative 3, and 4. I'm going to give you about a minute and a half to 2 minutes to try and come up with the solutions using the quadratic formula. All right, so go ahead and work it out, plug things in. Try and give me both the exact answers and the approximate answers with your calculator. If you have a question, let me know. If you don't want to see the answer ahead of time, just don't look up here, okay? How many of you are done? Okay. You can stop once you get to this point right here. You will not have approximate answers for this problem because it has an imaginary number. So we can stop at that point. While y'all are finishing that, I will All right, I think that's enough time. Everybody okay with getting this on the right side? Any questions on any of the numbers? You sure? When we have a negative under the root, that means that we're going to have an I in there, and as soon as you see I, you can stop. All right? As soon as you pop that I out of there, we're done. Because remember, what this means is that, like in the last problem, we got two answers, didn't we? We got like 1.65 and negative 0.15. So we can imagine those points lying on like a number line. These are imaginary numbers, and imaginary numbers do not lie on the number line. Right? So it wouldn't make sense for us to go try and find them. This is the way it would look if I did fractions, and you can just by looking at it, you can tell it's much uglier. But they are the same answer, even though they do not look the same. They are the same. I stopped right there, but you could get a common denominator between these two, and then take that and flip it, multiply by the reciprocal, like this. And then when you distribute this through, you get 3/8, and then there would be an 8 down there, and then that would be this. Just believe that it is. They are the same. Okay. All right, so I would say it was much easier to work with the one on the right, wouldn't you?
Yes, sir.
Okay. So my advice to you is that if you see a quadratic equation that has fractions, try and clear them first, and then work with these numbers. These numbers might be bigger than the numbers you had here, but they won't be fractions. All right. Pardon? What?
How did you convert it
To?
back to the other side?
Oh, to the one on the right? I multiplied this side by 4. I looked for the greatest common denominator,
Okay.
and then I passed that through. And when I got to here, that was 4x squared. When I got to here, I was multiplying 4 times 3/4. That's really like 4 over 1, and the 4's canceled, left me with a 3. Minus 3x. Yeah? All right. You ready? We're going to talk about graphs of quadratic functions. And these things called parabolas, or parabolas, right? So I always like to start, graphing quadratic functions to me is like one of the main things that I want a college algebra student to do. Like it's one of the, like in 13, 14. It's like one of the boxes that I like to see checked that we did, all right? And that we spent some time on, we understood. And the reason why I like it so much is because I think that it plays an important role in the real world, which I'm going to try and illustrate a little bit to you before we start going and graphing them. Give you a little bit of a reason why we'd want to study parabolas. So I'm going to go back to good old days, back when I'm going to get artistic here, okay? These are people. This is a castle. Okay? And there's people in here too. These people don't believe in the same things these people believe in. They disagree on the way they want to live their lives. So these people are going to storm this castle. They're going to take all their food. They're going to kill all the men. They're going to make all the women and children suffer for the rest of their lives, right? That's what they used to do back in the good old days. Right? So, but they built the castle to protect themselves from people like this, right? So these people want to attack that castle, so they start, throwing stuff at it, right? And as time went on, they got a little more advanced. They created like catapults, and they start launching stuff over there, right? Well, it turns out that when you throw something through the air, and we'll do this with the demonstration. Who wants to be on camera? You don't have to be on. Okay, can you just go over there? I'm going to try not to hurt you. Go that way. All right, go a little further. All right, right there. So we're just going to throw these markers back and forth to each other, right? So just, whoa, sorry. Just look at the path of the marker through the air, okay? So it doesn't matter how we throw it. I can throw it like that, or like that, or we can go, as high as I want. What's up, man? You're supposed to die for that. No, that's all right. Okay, that's it. Good, thank you. So no matter what, if you throw something through the air on a planet that has gravity, its path through the air is this curve, this curvy looking thing, right? And that curve is called a parabola. And there is some quadratic equation that models that. You know how, like, for every line we have an equation? For every parabola, there is an equation. So as time went on, we started to, people started to get smarter and study things, and they realized, look, this thing right here, we can just start launching stuff and we'll miss or we'll hit this wall, but we want to hit, right there where all the people are. We want to hit them. We want to make them feel our pressure, right? So they discovered that they could predict the outcome of the launch of their fireball, right? If they somehow knew the mathematics that was governing this sort of shape, right? And if you look back on like lines, with lines, we had these places where we hit the x-axis, right? We called those points, yes, but specifically the ones that hit the x-axis, we called those x-intercepts, right? Well, for every parabola, we have x-intercepts. And this point right here, where it hits, if you look at this as being the x-axis, right? And you have some y-axis over here, if this is the graph of this function, then this is the x-intercept. So if I know somehow the function, I can actually predict the x-intercept. And what I'll do is I will adjust my catapult so that I get the right function to have the correct x-intercept that I need to bring the castle down. Understand? Now that's kind of a morbid example of parabolas. So I'll do that one that's a little bit more user-friendly. We all use cell phones, right? Yes? You can't tell me you don't, right? All right, so everybody has cell phones. And when you're sitting here and you're in this classroom, right, in the building, you've got your phone on, and it's sending out a signal, right? So here's you in the classroom on the 3rd floor, standing up. And you've got your cell phone is sending out electronic signals in every direction. Every single one of our phones is doing that right now. In fact, if you could see it, like if you could see the electromagnetic radiation coming off of our phones, if you could see it, you'd be blind. There's so much of it in the room, right? So it's going everywhere, right? So what happens is somewhere around here, there's a tower. It's got these things on it. You've seen it, if you drive around, you see them, right? These cell towers. And so what happens is this tower is sending out signals, and it's also capturing signals. And so it goes, oh, hey, there you are, and then there's another tower over here, and then another tower, and then you got your friend that you want to call. And so this connection goes from here to here, across the tower, and then back down to that person. Or it might go to a building that has a computer in there, and that computer has Pokemon Go on it, and you're playing that little game. And everybody's feeding into that, right? Everyone's signals feeding in that. It's all interactive, right? So this is all signals just going around. The way they capture the signal, okay, the way they capture it is by using parabolas. So it turns out that if you've got these signals, so forget that picture for a second, if you've got these signals that are all everywhere, right? Going everywhere. And I have over here a parabola. And let's say it's like a metal dish, okay? A metal dish like this, shaped in the shape of a parabola. Then every signal that comes into here, every signal will hit, bounce, and when it bounces, it'll come back off like this, right? So they put this thing down the center of the parabola, and they put this little receiver on the end of it. So that signal goes, bounces, and goes right to that point. And every signal coming in will bounce and go to that point. It's because the perfect shape of the parabola forces all the signals to bounce to one single point. And that point is called a focus. So all of this electromagnetic energy is focused into one point, and then that's sent through the computer, and it's read, and it says, oh, you know, Robert's calling somebody, you know, and now I need to dispatch that signal out to the next tower, and it's all happening, you know, very fast. But it's the receiving of the signal that requires the parabolic dish to do it. If you just sat there, if you just put this out here like this, just put the receiver out there with no dish, then all these would just get lost. And you would have a very weak signal. So this is what happens when you drive somewhere. You're like, where the hell, man, my phone's not working, weak signal. The problem is that you're too far from the nearest dish, and not enough of your signal's making it into the parabola. Make sense? Okay. There's another example of this. If you've ever used a headlight on a car or a flashlight, right? It's just a bulb, right? It's just a bulb, but when you turn on your headlights, it looks like a beam. If you've ever driven through fog, right? You can see the beam of your light, and what's happening there is you have a light bulb, lights coming out in every direction, and behind the light bulb, inside the car, right, is this metal reflective material, like a mirror, and the shape of that is a parabola. And what happens is all the light coming out the backside, it's like the reverse of what we just said. It bounces and goes straight out. So everything bounces and comes straight out. All the light comes out like this. No matter where, it goes out straight. So we use that to focus a beam. And if you've ever had one of those fancy flashlights where you turn the flashlight and the beam spreads out and does that sort of thing, all you're doing when you're turning the flashlight is you're moving the mirror back and forth, and it changes where the focus is, and it messes it up basically. Instead of focusing it all into one beam, when you turn it, it moves it, and so you spread out the beam. Make sense? Okay. Was there anything else? That's good enough, right? Parabolas? All right. All right, so all parabolas, what notation are we going to use here? We know what lines look like. All parabolic functions look like this. So compare that to this, what you've seen before, right? That's a line. That's a line. Y equals mx plus b. We've graphed those, right? Everyone's comfortable with those, hopefully. Now we have a new equation. Here it is, and this is a quadratic function or a parabola. And if I graph this, okay, if I were to graph this, it's not going to look like a line, right? It's going to look like this thing I just showed you. It's either going to do this. It's like a big U or a big smile, or it's going to do this. In the case on the left, we say that it opens up. And over here, we say it opens down. Now, I know some of you have studied parabolas already. So what is it that will determine if it's the up or the down? It's a very simple thing that we look at. What is it? What positive or negative? You're correct. It's something is either positive or negative, but what part? Close. It's not the x squared, it's the number in front, the a. Okay? If the a in the problem is positive, it'll do this. So another way to say a is positive is to say a is greater than 0. Right? Bigger than 0 means positive. It'll open down if a is less than 0. A way you can remember that, it's kind of cheesy, but you can remember that a positive, right? Positive people smile. Negative people frown. Very simple. Okay? All right, there's also on both of these graphs an extremely important point. It's the lowest point on this graph, and it's the highest point on this graph. You see it? That point is called the vertex. Vertex. And this point is so special that we give it a special representation. It's a point, right? It has an x and y coordinate. But instead of calling it x and y, we call it h and k. And that's just to let you know it's that darn special. You get to be called something other than x and y, all right? You get to be called h and k. And this one, same thing. This would have an x coordinate of h and a y coordinate of k. So if you have a parabola that opens up, the vertex is the lowest point. If you have a parabola that opens down, the vertex is the highest point. Yes? Okay. Now we also have another thing happening here that we need to look at. And that is if you just draw a vertical line straight through the vertex, straight down, and over here, straight down. The parabola should be a mirror image of itself over that line. So if I take this side of the parabola and I reflect it over that, it should land right on top of the other side. And the same thing over here. So mirror image, you'll understand that? And same thing on this one. That line is called the mirror image line. No, it has a different name. It's called the Axis of Symmetry. All right? Axis of Symmetry. It's an axis, like the x-axis, y-axis. This is an axis of symmetry, where we have symmetric, the function is symmetric over that line, mirror image of itself. So axis of symmetry. Okay? Now, it's a vertical line, right? Vertical line? Vertical lines have equations. The equation of a vertical line is x equals some number. I don't know if you remember that. If I say x is 2, this means a vertical line through an x value of 2. So this has what is the x value of this line? What's the x coordinate of this line? Well, it goes through the vertex, doesn't it? So shouldn't it be the x coordinate of the vertex, which is h. So x equals h is the equation of the axis of symmetry. We're going to do an example of this and get all this information. I'm just trying to show you what these things look like. And then there's something else that we need to pay attention to that's going to require that I draw some different pictures other than what's right there. Let's talk about x-intercepts. How many x-intercepts does a line have? A line. we should have at most 1, right? Remember, if we have a line, 1 x-intercept, 1 x-intercept, right? Even if I draw a vertical line, 1 x-intercept. Is it possible to have none? If it's horizontal, it could, right? But the most I would have is 1. What about quadratic?
2.
It looks like I have 2, right? Look at this. I have 2 x-intercepts here, right? 1 there, 1 there. Here I have 2. So we could definitely have 2, right? We could have 2. I'll draw a picture here. We could have 2 x-intercepts. Is it possible to only have 1? Yes. What would that require? That the vertex is on the x-axis. So what if your vertex is right here on the x-axis and it goes up like this and up like this? Then you'd only have 1. Is it possible to have none? Yes. You could have a parabola that does this and your vertex is there and you'll never hit. Okay? So when it comes to parabolas, and we start talking about x-intercepts, there's 3 possibilities: 2, 1, or none. And it will be pretty easy for us to determine which of those it is. All right? We'll have to do a little work, but we'll be able to do it. The last thing that I'm going to talk about with these, as far as what they look like, is the Y-intercept. So what about the Y-intercept? Oh, you know what? No, because we need to talk about domain and range a little bit. Y-intercept. Is a parabola going to hit the y-axis? Does this one hit the y-axis? Yes. Yeah, right there. Does this one hit the y-axis? Yes. Yes, right there. Does this one hit the y-axis? Yes. This one? Yes. This one? Yes. Turns out for all parabolas, you are going to have one and only one y-intercept always. All right? Always one y-intercept. Always. All right. I think we're ready to start trying to graph this. Let's just kind of recap. Someone gives us a quadratic equation and they ask us to graph it. We know that the thing's going to either open up or down, right? It's going to have some point that's going to be either the highest point or the lowest point, that vertex. It's going to have either 2, 1, or no x-intercepts, and it's guaranteed to have one y-intercept, right? It'll have an axis of symmetry, which will be a vertical line, and domain and range, well, yeah, let's see if we can go without it for now, all right? Okay, here we go. I would like for us to sketch the following. We're going to start out with a pretty straightforward problem. Notice the instructions here. Sketch this. I want you to draw me a picture. And that does not mean we're back in high school where they told you to do everything on your calculator. All right? This means I want you to do it by hand. I want you to do the whole process by hand. So this is all about process. This is not about, man, I just need a picture of my computer can do that. I realize that. Okay? One of the bigger pictures in this class, Math 13, 14, is that you're learning to think critically, meaning learning to think through procedures. All right? First thing I'm going to do, what I'll do is over here I'm going to list out the steps. Some people really love to have steps, all right? So here are steps. You like steps or no? Yeah? Here are the steps. The first step, is this a parabola? I know that seems obvious, but if I'm asking you to sketch something, I could be asking you to sketch a line, right? Could be y equals mx plus b. Which means the steps are completely different. But if I'm asking you to sketch a parabola, here's what you should do. So first thing, is it a parabola? Question mark. Okay, it is. So I'm going to write over here, I'm going to go through this problem, I'm going to go through all these steps. So first thing, check mark, yes, it's a parabola. All right, second thing, up or down? Does it open up or down? Up, why? Because what's positive? Okay, it's up because A, which equals 1, is positive, right? I'm looking at this number right here, 1. Got it? All right, next step. Vertex. I would like for us to figure out that HK. I want us to figure out what it is. All right? I haven't shown you how to do that, have I? There is a formula to find H and K. The formula comes from calculus. In calculus, we actually come up with a formula. And then here we pass it on to the people in algebra and say, go ahead, use this. It's very convenient. So here's the formula. The H that you're looking for, right, H is part of it, is negative b over 2a. Always. Now when I say negative b over 2a, I'm referring back to this idea that this is ax squared plus bx plus c, right? So the a is the 1, the b is the negative 4, the c is the negative 5, just like it was when we were using quadratic formula. So we just compute that, bless you. That'll give you your h. Now we still need k, all right? So to get k, what we do is we plug h into equation for x. And that's going to be the k. So I'm going to do that work right here. I'm going to do step 3 right here. Vertex, h will be, all right, be very careful here. Negative b, right? Negative b divided by 2a. What is negative b for us in this problem? B is negative 4, right? What's negative b? Positive 4. So remember in the quadratic formula we had to be careful with that also? Right? Same thing here. This is going to be, I'll write it down. It's negative, right? But then b is negative 4. And then divide that by 2 times what's a? 1. So that's actually positive 4 over 2, which is just 2. Agreed? Okay, that's h. Now to get k, we're going to plug that value that we just got into the original equation for x. I'm going to replace this with what?
2.
That with 2. Figure out what that is. That's k. So k is equal to this 2 plugged in and squared minus 4 times 2 minus 5. Understand what I did there? Okay. This turns out to be 4 minus 8 minus 5. Should be negative 9. So our vertex in this problem for this parabola is the point to negative 9. Understand? Okay, we still got more to do. All we have right now, all we can say is that this parabola opens up, and I know what it would be the lowest point or highest point on this one. Lowest point, I know this is the lowest point on the graph, yeah? What I still would like to recover from this is I want the X-intercepts, right? So I can get a better picture, of a more accurate drawing of this parabola. I want the X-intercepts and the Y-intercepts. So let's talk about X-intercepts. How many X-intercepts will we have? Well, there could be 2, 1, or none, right? Right? You said 2. Are you working ahead, or you just?
It's down below the.
Yeah. Okay. So when we go for the X-intercept step, here's what I suggest you do. All right, this is going to be in the steps here. Step 4, at this point right now, I want your step 4 to be a quick sketch. I want you to do a quick sketch, just real fast. So here's my step 4. Where's the vertex? 2, -9. That means I go to the right 2 and down 9. Look, I'm not even being accurate with that, right? Just it's to the right 2, down 9, yes? Which way does this parabola open? Up or down? Up. So if it opens up from here, it looks like a U, then it's going to have to go something like this, right? How many x-intercepts do I have? I have 2. Do you see that? So this quick sketch is just for the purpose of determining how many x-intercepts I should have. Got it? So step 5, after the quick sketch, is to answer the question, how many x-intercepts? If 1 or 2, then solve ax squared plus bx plus c equals 0. If none, move on. All right, so this step is saying, all right, looking at your quick sketch, how many x-intercepts do we have? We said we had 2. If you have 1 or 2, then you actually have to take your quadratic and set it equal to 0. Why? Why do I do that?
Solving for x.
We're solving for x, right? But isn't putting a 0 here the same as replacing y with 0? And isn't that how we find x-intercepts? If you want to find the x-intercept, you let y be 0. If you want to find the y-intercepts, you let x be 0. Remember that from lines? Same thing here. I want to find the x-intercept, so I replace y with 0. If I replace y with 0, then we're doing the problems that we were doing at the beginning of class, right? Quadratics equal to 0. So do you see how quadratics being equal to 0 from earlier in last class ties into this? Okay, so let's go ahead and do it. Step 5 for us, I have how many? 2, right? Step 5, I have 2 x-intercepts. So I'm going to set the function equal to 0. Now, look, as long as I've been teaching, no book or other instructor or tutor that I've ever talked to does it this way. So if you go get help in tutoring lab, I'm most certain they're not going to tell you to do this, all right? What most of the time what they will do is no matter what, when they go to find the x-intercepts, they'll just set this up and solve it, all right? And they're either going to get 2 answers, 1 answer, or no answers. How would someone who didn't do this step know that it's no answers? Guess what happens when they solve this? You get the I. You get the I in there. So if you get the I in there, that means you have no answers, no x-intercepts. By doing this quick sketch in this